The polar vortex, that will determine Earth's fate. The North and South poles of the Earth are two enigmatic places full of great mysteries. There are meteorological phenomena that do not occur anywhere else on the planet, and although it sounds like a conspiracy theory or science fiction movie, at the poles of the Earth there are two massive, icy menace walls that protect us from an ice threat that has claimed many lives throughout human history. But don't worry, before you start imagining huge walls of ice and giant creatures that threaten the human race, you should know that we're talking about an invisible wall of air, not a wall of ice, and by threats, we don't mean creatures but incredible atmospheric phenomena. Do you want to know what an invisible wall is and what atmospheric phenomenon we're talking about? Come find out with us. The polar vortex, the fear of ice. The threat mentioned at the beginning of this video is an atmospheric phenomenon known as a polar vortex, which is a large-scale persistent cyclone that is located in the polar areas of the Earth, and it is one of the most terrifying, and it must be treated with caution because it has claimed many lives throughout history. Two polar vortices exist, one in the north and one in the south. The Antarctic polar vortex is more pronounced and persistent than the Arctic vortex because the distribution of land masses and high latitudes in the northern hemisphere causes an increase in Rossby waves, which help break the vortex and cause it to move out of the regions where it is normally found, whereas the vortex in the southern hemisphere is less affected because it is concentrated almost entirely over Antarctica. Rossby atmospheric waves are caused by vortex power conservation and are influenced by the Coriolis force and pressure gradient. The Coriolis force causes fluids such as the atmosphere to rotate to the right as they move in the northern hemisphere and to the left in the southern hemisphere due to the rotation of the Earth. A fluid going from the equator to the North Pole, for example, will be redirected to the east. A fluid moving from the north to the equator will be diverted to the west. This is one of the reasons hurricanes form and why they spin in different directions depending on whether they form in the north or south. Polar vortices are strongest in the summer and weakest in the winter. When the polar vortex is weak, extratropical cyclones traveling to higher latitudes can disrupt the single vortex by producing smaller vortices within the polar air mass. Each polar vortex is separated into two sections, the tropospheric polar vortex at an altitude of 10 to 15 kilometers and the stratospheric polar vortex above 50 kilometers. The two polar vortices are always revolving in the same direction as the Earth, and winds can reach speeds of up to 240 kilometers per hour. Consider that gusts above 120 kilometers per hour are already classified as hurricanes. Do you think this is actually impressive? The main puzzle, though, is how these cyclones can exist near the Earth's poles. Why don't they stop? And the solution to those questions is simple: the difference in temperature. Because the Earth is a spherical that revolves on itself, the amount of sunlight it receives from the sun is not uniform, as the planet's equator always receives more solar energy. The air in the atmosphere close above the equator warms up more than the air at the poles because it receives more heat. This causes low pressure, which occurs when the air heats up. On the other hand, if the air cools, the opposite occurs, high pressure. Because everything is due to the Earth's thermodynamics. Because cold air occupies less space, when a mass of air cools, it can compact and take up less space. By taking up less space, there can be more air particles in the same spot, causing that area to have a higher pressure because there is more mass. In the contrary instance, when air heats up, it takes up more space, the particles separate, and the pressure in that area drops since there are less particles. In conclusion, cold air creates high pressure while hot air causes low pressure. What is the connection between this and the polar vortex? It's that easy. Remember how we talked about the air in the equatorial atmosphere? Because the air at the equator has a lower pressure than the air at the poles, cold air from the polar vortex should constantly prefer to travel towards the equator because there is more space here, but this does not happen. For what purpose? What prevents the vortex from traveling to the equator? We'll get to that later, but for now, remember that when the Arctic vortex is at its fiercest, there is only one vortex. Still, the Arctic vortex is typically elongated, with two cyclonic cores, one over Baffin Island in Canada and the other over northeastern Siberia. When the Arctic pattern is at its weakest, subtropical air masses can travel poleward, forcing Arctic air masses to shift toward the equator, as seen during the 1985 winter Arctic outbreak. Polar vortices can reach extraordinarily low temperatures, as low as -50 degrees Fahrenheit, which makes them exceedingly dangerous. A profound cold wave affected most of the United States and Canada around the end of January 2019, and it is now known that it was caused by breakouts of cold air from the Arctic induced by a weaker polar vortex. The United States National Weather Service warned citizens not to go outside because it was possible to freeze in just 10 minutes in these temperatures. Hundreds of colleges, institutes, and universities were closed in the affected areas, but in the end, around 21 people died from severe frostbite in the United States alone. The polar vortex is thought to have had an impact on Europe as well. For example, the polar vortex that delivered strong cold to the United States and Canada is blamed for the 2013-14 winter floods in the United Kingdom. The polar vortex has produced waves of harsh cold throughout history, almost usually ending many people's lives. But if the polar vortex is so harmful, how have we managed to avoid it thus far? The polar night jet, also known as the jet stream or jet currents, are the invisible walls that shield us from polar vortex. Jet streams can begin, terminate, split into two or more pieces, unite into a single stream, or travel in many directions, including the opposite direction of the rest of the jet. Jet streams are the result of two factors: solar radiation heating the atmosphere, which forms large-scale polar circulation cells, Ferrel and Hadley, and the Coriolis force acting on these moving masses. The large-scale flow of air throughout the Earth is represented by the Ferrel and Hadley polar circulation cells. They are strongly tied to the tropics because the movements of air masses originate in these locations. The Coriolis force, on the other hand, is created by the planet's rotation on its axis and is the same force that causes storms. Internal heat, rather than solar heating, drives the jet streams of other worlds. The polar jet stream forms near the junction of the polar circulation and the Ferrel cells, whereas the subtropical jet forms near the junction of the Ferrel and Hadley circulation cells. In layman's words, these heated jet streams run from the equator to the poles in the tropics, hitting head-on with the frigid air currents of the polar vortex. When two massive air masses clash, they do not mix, but rather rise or fall and then return to where they came from. As a result, the polar vortex remains locked and restricted to the pole, unable to escape. The polar night jet is that invisible wall mentioned at the beginning of the video. The jet currents that cover the entire planet and are distributed throughout the Earth are our greatest allies. Without this, the polar vortex would emerge more frequently from his region, causing waves of intense cold in the northern countries. So far, we've covered everything that happens as a result of the North Polar Vortex, but what about the South? The polar vortex in Antarctica experiences the same fluctuations as the one in the north, with the exception that the one in the south is far more stable. This is due to the Southern Ocean separating Antarctica's surface landmass from the rest of the planet. This ocean's temperatures keep Antarctica and the southern polar vortex separated. It has been shown, however, that it can also break and bring cold waves to countries near the South Pole. Another distinguishing feature of the two vortices is that, whereas the northern vortex has an elongated structure, the southern hemisphere Antarctic vortex is a single area of low pressure located along the border of the Ross Ice Shelf, around 160 west longitudes. When the polar vortex is powerful, winds at the surface level intensify and remain between 30 degrees and 60 degrees west latitude. When the polar vortex weakens, high-pressure zones in the mid-latitudes can push toward the pole, causing the polar vortex, jet stream, and polar front to migrate toward the equator. The jet stream bends and deflects southward. This causes cold, dry air to suddenly collide with warm, moist mid-latitude air, resulting in a sudden and dramatic change in weather known as a cold snap. In Australia, a polar vortex, also known as a polar gust or polar plunge, is a cold front that pulls in air from Antarctica, bringing showers, snow, usually inland, with blizzards in the highlands, winds, gusty ice, and hail to the country's southeast, including Victoria, Tasmania, the southeast coast of South Australia, and the southern half of New South Wales. The threat is constantly present. Although jet streams protect humans from polar vortices, it is increasingly being found that polar vortices frequently break up and depart their zones, particularly in the northern hemisphere, where the vortex is not uniform. These occurrences are becoming more often as a result of climate change and global warming. The invisible wall that protects us from the threat of ice, jet streams, deteriorates as the planet's temperatures change. As the planet's temperature rises, even little, our defense wall weakens, allowing some of the cold from the polar vortex to enter. Currently, these events are not as serious or as diverse as they have historically been, but if we do not take care of our planet, the jet streams will cease to protect us. If things continue as they are, it is feasible that in the future, many years from now, our protective wall may entirely fail, and the Earth will enter a new ice age. For the time being, the effects of climate change can be seen in certain parts of the world, but it is not too late. We have enough time to continue researching these fascinating phenomena and, in the process, learn to live more in harmony with our planet and comprehend our place in it. And you, how much do you know about polar vortices and jet streams? Let us know what you think in the comments.